Superposition and interference. Superposition states that when two or more waves overlap, the resultant displacement at any point is given by the vector sum of the individual displacement. When the two waves actually overlap, you can see that the amplitude actually add up, hence demonstrating that it is a vector sum of the individual displacement. Now let us take a look at the term interference. Interference is a combination of separate waves in the same region of space to basically to produce a resultant force called interference. There are two types of interference. One is called constructive interference. Constructive interference occurs when the trough or the crest are in the same phase. Hence, the amplitude is the sum of the amplitudes of two of the waves. And when that occurs, we state that the waves are in the same phase. When that occurs, waves are in the same phase. And the path difference between them is n lambda. Destructive interference. Destructive interference occurs when the crest meets the trough. When the crest meets the trough, or the trough meets the crest. In this case, the amplitudes of the two waves will cancel each other, and the final amplitude is 0. So that occurs when waves are when waves are in antiphase. And when waves are in antiphase, the path difference is odd number of wavelength, which is lambda over 2, 3 lambda over 2, and 5 lambda over 2, and 7 lambda over 2, and so on and so forth. Next, we look at the definition of coherent sources. Coherent sources share the following, which means they have the same constant phase difference and they have the same frequency. Coherent sources therefore can produce constructive and destructive interference when the path difference is n lambda or 2n plus 1 half lambda. Let's take a look at observable wave interference. The conditions for constructive and destructive interference of waves to be observed is when the amplitude of the waves are the same and the sources are coherent, which means they share the same phase difference and they have the same frequency. And finally, for transverse wave to display observable wave interference, they must be plane polarized and both waves must be on the same plane. So for example, what you see down here is that you have two sources, S1 and S2, which are coherent. They produce wave of equal amplitude. So for example, like this point, which is actually equal distance from S1 to S2. So the path difference is 0. So in this case, the red dot signifies that it is actually a constructive interference. Now let's take a look at the blue dot. So in this case, the path difference to this point must be odd half lambda. The path difference to this point must be is when there's actually a destructive interference, which means is actually 2n plus 1 half lambda over 2. The line that joins all the points where constructive interference occurs is termed as the antinodal line. So in this case, aside from A0, you also have your A1, and in between them, the dotted line joins all the points where destructive interference occurs. So N1 is termed as the nodal lines. Next, we look at the definition of coherent sources. Coherent sources share the following, which means they have the same constant phase difference and they have the same frequency. Coherent sources therefore can produce constructive and destructive interference when the path difference is n lambda or 2n plus 1 half lambda. So in the A level, you're supposed to be able to reproduce this sketch and also label the antinodal and the nodal lines. With that, let's take a look at an example for constructive and destructive interference. Down here, you actually have a source. The source is actually beaming radio waves that hits what they term as actually a heavy side, which will be able to reflect the radio wave. S prime is actually the receiver. So in this case, the S prime will be able to receive the radio waves from two different paths. The first path is from S, where the radio wave will travel direct to S prime. Alternatively, the radio waves will travel along the path along L, and after that get reflected and travel a distance of L to reach S prime. Based on the fact that the emitter S is 80 km away from the atmosphere and the receiver is actually 120 km away, we can actually use this as a we can use this as a right angle triangle using Pythagoras theorem to derive that L is actually 100 kilometers. Hence, the path difference, as what we said earlier, is actually to sum the 2L. So it's 2L minus by D. So in this case, it happens to be 80 kilometers. So that is the path difference. So say, for example, if the wavelength of the radio wave is 200 meters, then the path difference is 80,000 meters. We let that, and if constructive interference occurs, then we let that be N1 lambda, and lambda is 200 meters. So your N1 will end up as 400, and we can safely conclude that constructive interference occurs when the radio waves has a wavelength of 200 meters. So in order to have destructive interference, let us now change the wavelength. So in this case, the path difference remains as 80,000 meters, but it's equal to 2m plus 1 lambda over 2. So this is what we mentioned, your odd number half lambda, like half lambda, 3 lambda over 2, 5 lambda over 2, 7 lambda over 2, so on and so forth. So in this case, n is integer, so we assume that if n is 200, then one of the wavelength that can produce a destructive interference at the receiver S prime is 399 meters. Finally, if the radio waves that's emitted changes its wavelength from 200 meters to 180 meters, what is the number of maxima that it will go through? So in this case, what we do is that we can calculate when lambda is 180, we will work out that N2 is 444.4. So in this case, when originally the wavelength is 200 meters, we're starting from N1. So from N1 to N2, we know that for the first maxima is when N1 becomes 401. And from there, we can continue counting, which means that we will end up with a total of 44 maxima. So the 44th maxima will be when N is actually equal to 444. So what happens if we decide to change the question and say that if the wavelength decreases from 200 meters to 180 meters, we decide to find out the number of minima. So in this case, the path difference is still 80,000 meters. It will now be equal to 2m plus 1 lambda over 2. We'll now substitute lambda as 200 meters, and we'll find that N1 is 399.5. When we substitute lambda as 200 meters, the N2 will be 443.9. So in this case, from N1, which is 399.5, to this, starting from N1, which is 399.5, the first minima will actually be 400, followed by 401, and so on and so forth until 443. So therefore, because of that, it will be 43 plus 1. Therefore, the number of minima that will be observed at x prime when the wavelength decreases from 200 to 180 meters will also be 44.